Something is wrong with the sky, not in a way you can see with your eyes, not in a way that shows up on the evening news with dramatic graphics and a countdown timer. It is wrong in the way that only becomes visible when you spend years staring at data, when you line up what your instruments are telling you against every equation you have ever trusted, and the numbers simply do not match. Meteorologists around the world have spent the last several years documenting atmospheric behaviours that their best models say should not be happening. Not behaviours that are unusual or statistically rare. Behaviours that, according to the fundamental physics underpinning how our atmosphere is supposed to work, are physically impossible. And yet there they are, showing up in the data, repeating themselves, demanding an explanation that nobody has been able to give. This is the story of what is happening above our heads right now, why the scientists who study it are genuinely unsettled, and what it might mean for every living thing on the surface of this planet. To understand why any of this is strange, you need to understand what meteorologists thought they knew. For over a century, the study of Earth's atmosphere has been built on a set of physical laws that were considered as solid as anything in science. The way air moves, the way heat distributes itself, the way moisture travels from the ocean surface to the clouds above your head. These were not guesses. They were principles tested against thousands of observations, refined over decades, encoded into the most powerful supercomputers ever built. When a meteorologist runs a forecast model, they are essentially solving an enormous physics problem, and for most of the history of modern meteorology, those solutions were good. Not perfect, but good. Good enough to trust with billions of dollars of infrastructure, with the lives of people in the path of storms, with the agricultural systems that feed the world. That trust has started to fracture. The first cracks appeared quietly, the way cracks usually do. Researchers began noticing in their post-event analyses that certain extreme weather events had behaved differently than their models predicted, and not just in the ordinary way that weather surprises forecasters. Weather is always imprecise at the edges. Wind gusts a little harder than expected. A storm shifts 10 miles to the north. That is normal. What was not normal was that some of these events seemed to have violated the energy budgets that govern atmospheric dynamics. There was more heat energy in certain systems than there should have been, given the inputs the models could account for. There was more moisture in the upper atmosphere than the known sources could explain. There were circulation patterns forming at altitudes and in configurations that the equations of fluid dynamics, equations that have successfully described the behavior of fluids for nearly 2 centuries, suggested were not stable and should not persist. They persisted anyway. One of the most troubling observations involves what scientists call the stratospheric water vapor anomaly. The stratosphere is the layer of the atmosphere that sits above the weather, above the clouds. Above most of the turbulence of daily life, it is extraordinarily dry. It has always been extraordinarily dry. The physics of how water vapor moves through the tropopause, the boundary between the lower and upper atmosphere, acts as a kind of cold trap, freezing out almost all of the moisture before it can rise into the stratosphere. This is not a quirk or an approximation. It is a robust physical mechanism that has been understood and measured since the middle of the 20th century. In recent years, instruments carried by balloons and satellites have found water vapor concentrations in the stratosphere that should not be there. Not slightly elevated, dramatically elevated. Concentrations that exceed what the known transport mechanisms can deliver by margins that have forced scientists to seriously ask whether their understanding of that cold trap is somehow wrong, or whether something else entirely is injecting moisture into the stratosphere from a source, or through a process they have not identified. The initial hypothesis was volcanic. A large enough eruption can punch water vapor directly into the stratosphere, bypassing the cold trap entirely, and there was indeed a significant eruption in the Pacific in early 2022, an underwater volcano near the Tonga archipelago that sent a column of water vapor into the stratosphere in an amount that researchers described as historically unprecedented for a volcanic event. Some scientists argued that this single eruption could explain the anomaly. But as the years have passed and the measurements have continued, the elevated concentrations have persisted long past the point where the Tonga contribution should have dispersed and dissipated. The volcanic hypothesis cannot account for all of it. Something else is going on. There is a parallel anomaly in the ocean, and it is intimately connected to what is happening in the sky above it. The surface temperatures of the world's oceans have been running at levels that have repeatedly broken the records that scientists use as their baseline for understanding normal variability, not by fractions of a degree, which would be unsettling but comprehensible within the framework of gradual warming, by full degrees in some regions, by amounts that the models, even those that account for the long-term trend of warming, struggle to reproduce. The North Atlantic in the summer of 2023 was so anomalously warm that a team of European researchers published a paper with a title that essentially asked whether something in the fundamental understanding of North Atlantic heat exchange had broken down. Ocean surface temperature matters enormously for the atmosphere, because the ocean is where the atmosphere gets its energy. Heat evaporates water, water vapor rises, energy transfers. The atmosphere is in constant conversation with the ocean surface beneath it, and when the ocean surface does something the models do not expect, the atmosphere does something the models do not expect in response. What made the 2023 anomaly so disturbing was not just its magnitude, but its geography. It was not uniformly distributed in a way that matched the spatial patterns of known drivers like El Niño. It was concentrated in regions and in configurations that suggested something more localized, more structural, more difficult to attribute to any single known cause. Some researchers pointed to a reduction in aerosol pollution following new international shipping regulations that took effect in 2020. Ships burn fuel. Fuel produces sulfur particles. Sulfur particles in the lower atmosphere reflect sunlight back into space. And for decades, the shipping lanes of the world's oceans had been pumping enough of these particles into the air to create a kind of accidental, unintended cooling effect. When the regulations forced a dramatic reduction in sulfur emissions from shipping, some scientists argued that this cooling mask was removed, allowing the underlying warming signal to emerge more fully. It is a plausible mechanism. The numbers roughly work in terms of order of magnitude, but even accounting for the shipping aerosol reduction, the models still cannot fully explain the temperature anomalies that have been observed. There is a residual, an unexplained remainder, and in science, an unexplained remainder is the thing that keeps you up at night. What makes the atmospheric anomalies particularly unnerving to the people who study them is that they are not occurring in isolation. They are occurring simultaneously, in different parts of the atmosphere, at different altitudes, in different physical systems, and they all seem to be pointing in the same direction. More energy, more moisture, more instability, more deviation from what the physics predicts. The jet stream, that river of fast-moving air high in the troposphere that acts as the steering mechanism for weather systems across the middle latitudes, has been behaving in ways that meteorologists describe with words like erratic, unprecedented, and deeply strange. The jet stream has always had natural variability. It meanders, it forms waves. But those waves have historically been constrained by the physics of the rotating Earth, by the temperature contrast between the tropics and the poles that drives the jet's energy. As that temperature contrast has shifted, as the Arctic has warmed significantly faster than the tropics, something in the behaviour of the jet stream appears to have crossed a threshold. There have been episodes in recent years where the jet stream has essentially stalled, sitting in a configuration that amplified its natural waves to an extraordinary degree, locking weather patterns in place for weeks at a time in a way that allowed extreme events to intensify far beyond what a more mobile jet stream would have permitted. Heat waves that should have been moderated by the normal progression of weather systems instead became self-reinforcing, the stalled jet holding hot air in place while it continued to absorb energy. Flood events that should have been short-duration affairs instead became week-long catastrophes as the same atmospheric circulation continued to pump moisture into the same region. And here is the piece that troubles atmospheric scientists most deeply. The models do not predict this stalling behaviour with any reliability. They can simulate it after the fact. Once researchers know what happened and can tune the conditions, but their ability to forecast it in advance, to warn that a jet stream stall is coming, and that a heat wave will therefore last 3 weeks rather than 3 days, remains severely limited. The physics that governs jet stream behaviour is not subtle or poorly understood in a general sense. The equations have been in the textbooks for decades, but something about the way the real atmosphere is solving those equations right now is producing answers that the textbooks did not anticipate. There is a concept in fluid dynamics called a bifurcation point. A system can operate in a stable regime, behaving in predictable ways that return to a baseline after being perturbed, and then, when some parameter crosses a critical threshold, the system can jump to a completely different regime, a different set of behaviours, different attractors, a different kind of stability that looks nothing like what came before. Climate scientists have been warning for years that the Earth's climate system contains potential bifurcation points, thresholds beyond which the system's behavior would change in ways that are difficult or impossible to reverse. What the atmospheric observations of the last few years have forced some researchers to ask quietly but seriously is whether we are watching certain parts of the system approach or cross one of those thresholds right now. The honest answer is that nobody knows. That is not a satisfying answer. It is not the kind of answer that fits neatly into a news cycle or a policy debate, but it is the truth. The scientists who study this are not hiding certainty behind cautious language. They are genuinely uncertain, and their uncertainty is itself informative, because these are people who have spent their careers building the most sophisticated models of atmospheric behavior that have ever existed, models that run on some of the fastest computers in the world, and those models are failing to capture what they are observing. Let's talk about one specific example in detail, because abstractions about models and anomalies can only carry so much weight. In the summer of 2021, a heat dome settled over the Pacific Northwest of North America, over the coast of Canada and the American Northwest. The region is one of the most temperate on Earth. It has a maritime climate, moderated by the ocean, and its historical temperature records reflect centuries of relatively mild summers. The town of Lytton, British Columbia, a small community in the interior of the province, had a historical temperature record of just under 41 degrees Celsius. On the 29th of June, 2021, Lytton recorded 49.6 degrees, the entire country of Canada's highest ever recorded temperature, shattered by nearly 5 degrees in a single afternoon. When atmospheric scientists ran their models backward to try to understand how that event was possible, they found something that genuinely startled them. The heat dome itself was an extreme but not incomprehensible event. Heat domes form when a ridge of high pressure becomes stationary and allows air to compress and heat as it descends. What was not comprehensible was the magnitude of the temperatures underneath it. The models that were given the actual atmospheric conditions of that event, the pressure gradients, the moisture profiles, the wind fields, consistently produced maximum temperatures that were several degrees below what was actually observed. The real atmosphere was getting hotter than the physics, as the models understood it should have allowed. One explanation that has gained traction involves a phenomenon called soil moisture feedback. When the ground is dry, incoming solar energy heats the surface directly. When the ground is moist, some of that energy goes into evaporating water rather than heating the surface, which caps the temperature increase. The Pacific Northwest had experienced an unusually dry spring in 2021, and the soil moisture deficit may have removed the evaporative buffer, allowing temperatures to climb higher than they would have with normal soil conditions. This is a known mechanism. It is in the models, but even with it fully accounted for, the observed temperatures still exceeded what the models produced. There is a residual. There is always a residual. The residual matters because it means the feedback between the surface and the atmosphere. The way heat builds and recycles in a stalled weather system is more amplified in the real world than in the models. And if the feedbacks are more amplified than the models think, then every forecast of future extremes is an underestimate. Not by a small amount. Potentially by a lot. This is not a comfortable conclusion for anyone involved. The scientists who work on these models have dedicated their careers to making them as accurate as possible. The policymakers who use model output to design infrastructure and emergency response systems need those models to be reliable. The reinsurance industry, which prices the risk of catastrophic weather events, depends on probabilistic forecasts that assume the models capture the tail of the distribution, the rarest and most extreme events. If the tails are fatter in reality than in the models, then the risk calculations are wrong, and the consequences of that wrongness will be measured in lives and in the solvency of institutions built on the assumption that the worst case was something a model could have predicted. There is another anomaly worth examining in detail, and it lives not in the heat of the lower atmosphere but in the cold of the upper atmosphere, in a layer called the Mesosphere, which sits between roughly 50 and 85 kilometers above the surface. The Mesosphere is the coldest place on Earth in terms of temperature, with average temperatures plunging to nearly negative 100 degrees Celsius. It is so cold and so thin that it is barely understood. Instruments rarely venture there. Satellites orbit far above it or peer at it obliquely. But what instruments have observed in the Mesosphere over the last 2 decades is a trend toward lower temperatures, colder than they should be, and an increase in a phenomenon called noctilucent clouds. Noctilucent clouds are formations of ice crystals that form at extreme altitudes when the temperature is cold enough and when there is enough water vapor present to freeze into crystals. They glow because they catch sunlight long after the sun has set below the horizon for observers on the ground, producing an ethereal bluish-white shimmer in the twilight sky. They were historically rare, observed only at high latitudes, only during the summer months, only under very specific conditions. They have been getting more common, more widespread, more visible at lower latitudes than they have ever been recorded before. Observers in Europe and the United States who have never seen them in their lifetimes are seeing them now. The physics of noctilucent clouds requires water vapor at extreme altitude and extreme cold. As the mesosphere cools, more ice can form. But where is the water vapor coming from? The cold trap at the tropopause should prevent water vapor from reaching the mesosphere in significant quantities. The same anomaly showing up in the stratosphere seems to be extending all the way to the edge of space. Something is transporting moisture through the atmosphere in ways that the models do not capture, in quantities that the known mechanisms cannot explain. One hypothesis involves the breakdown of methane at high altitudes. Methane in the upper atmosphere reacts with oxygen radicals, and one of the products of that reaction is water vapor. As methane concentrations have increased in the lower atmosphere due to agricultural and industrial emissions, more methane reaches the upper atmosphere, and more water vapor is produced at altitude. It is a plausible mechanism, and it would produce a gradual, sustained increase in upper atmospheric water vapor over the decades. But the rate of increase in noctilucent cloud activity and in mesospheric water vapor appears to be accelerating beyond what simple methane chemistry would predict. What all of these observations share, from the anomalous stratospheric moisture to the ocean's surface temperatures, to the jet stream stalling to the Pacific Northwest heat dome, to the spread of noctilucent clouds, is a quality of excess. The real atmosphere is doing more than the models predict. More heat, more moisture, more instability, more extreme. And the margins of excess are not small. They are large enough to matter, Bray. Large enough that scientists are publishing papers with notably cautious language about whether the current generation of climate and weather models is capable of capturing the dynamics of the world that is actually forming above our heads. There is a phrase that appears in several of these papers, offered quietly, almost apologetically as a conclusion. The authors note that their models appear to be missing feedbacks. Feedbacks are the self-reinforcing loops in complex systems, the ways that a change in one part of the system circles back and amplifies or dampens changes elsewhere. The climate system is full of feedbacks. Some of them are cooling, the kind that resist change and stabilize the system. Some of them are warming, the kind that amplify change and push the system further from its starting point. The models include the feedbacks that are known and understood. The concern is that there are feedbacks operating in the real atmosphere right now that the models have not adequately characterized, feedbacks that are making the system more responsive to perturbation, more volatile, more capable of producing extreme events at a frequency and magnitude that exceeds what any historical record or model projection suggested was possible this soon. What does this mean in practical terms for the people who live under this sky? It means that the mental models most people carry around, the intuitions built from decades of lived experience with weather, are increasingly unreliable. The summer that was always hot might now be extreme. The river that flooded occasionally might now flood catastrophically. The fire season that once started in late summer might now begin in spring and extend past the first snowfall. These are not predictions offered with false precision. They are descriptions of trends that are already underway, already measurable, already showing up in insurance claims and in hospital admissions and in agricultural yield reports. It also means that the forecasting systems that communities depend on for early warning are facing a fundamental challenge. A forecasting model can only warn you about what it knows how to predict. If the physics governing an extreme event includes processes that the model does not capture, the model will underestimate the event and the warning will come too late or in too mild a form to motivate the response the event actually requires. The scientists who run these models are working urgently to close the gaps. New parameterizations of convective processes, better representations of land surface feedbacks, higher resolution simulations that can capture phenomena that coarser models smooth over. The pace of improvement has been remarkable, but the atmosphere is not waiting for the models to catch up. There is a deeper philosophical question embedded in all of this, and it is worth sitting with for a moment. The scientific framework for understanding the atmosphere was built on the assumption that the atmosphere is a physical system governed by knowable laws, and that given sufficient data and computational power, those laws can be used to predict its behavior. This assumption has been enormously productive. It gave us weather forecasting, it gave us climate science, it gave us the ability to plan cities and infrastructure around expected extremes. What the anomalies of the last few years are testing is not whether the physical laws themselves are wrong. They are not. The equations of fluid dynamics and thermodynamics remain as valid as they ever were. What is being tested is whether the parameterizations, the approximations and simplifications that allow those equations to be applied to a system as complex as the global atmosphere are adequate for the world that is emerging. Researchers who study tipping points and nonlinear dynamics in complex systems have a phrase for what happens when a system that has been well described by a set of approximations begins to behave in ways the approximations cannot capture. They call it leaving the regime of validity. The approximations were valid for a certain range of conditions. Outside that range, they break down. The honest question that some atmospheric scientists are beginning to ask is whether the changes in the climate system have pushed parts of the atmosphere outside the regime of validity of the models that were built to describe it. They were not wrong that something in the models was wrong, they were wrong about what it meant. In 2023, Antarctic sea ice reached its winter maximum at a level so far below the previous record that the scientific community struggled to find the right language to describe it. The anomaly was not at the edge of the distribution of expected values, it was outside the distribution entirely. Some researchers described it as a once in a 7.5 million year event if you assumed the statistics of the previous 45 years continued to hold. That number was not a confident estimate. It was an expression of how far outside the known range the observation had fallen. When the probability is that small, the number stops being a meaningful prediction and starts being a way of saying, we have no framework for this. The ice did not recover. The following year, the anomaly persisted. The winter maximum remained far below the historical baseline, and the scientific community began, carefully and with appropriate hedging, to ask whether what they were seeing was a step change, a rapid transition from one state to another, rather than an extreme fluctuation around a stable mean. That distinction matters enormously. A fluctuation implies the system will return to its previous behavior. A step change implies it will not, at least not on any timescale relevant to the decisions human beings are making right now. And the difference between those two interpretations has consequences for everything, from sea level projections to ocean circulation models, to the behavior of the atmospheric systems that draw energy from the contrast between ice-covered and open ocean surfaces. What caused it? The honest answer is that the full explanation is still being worked out. There are candidate mechanisms, changes in wind patterns over the Southern Ocean, the intrusion of warmer water at depth under ice shelves, the possible influence of the Hunga Tonga volcanic eruption in 2022, which injected an extraordinary amount of water vapour into the stratosphere and may have altered the radiative properties of the atmosphere in ways that are still being traced through the data. There is also the underlying warming trend, which had been loading the system with energy for decades, and which the previous period of stability had, perhaps, been temporarily masking. The fact that there are multiple candidate mechanisms is itself informative. It means the event was not caused by a single unusual forcing that can be identified, bracketed and set aside. It means multiple parts of the system were moving in the same direction at the same time, and their effects compounded. That kind of compound behavior is exactly what the models have historically struggled to capture, not because the individual mechanisms are unknown, but because the interactions between them, the way they amplify or suppress each other under specific conditions, are difficult to represent accurately. There is a term researchers use for this: emergence, properties that emerge from the interaction of components that cannot be predicted by studying the components in isolation. The atmosphere is an emergent system at every scale, from the formation of individual clouds to the organization of storm systems, to the behavior of the jet stream to the way energy moves between the tropics and the poles. The models capture some of this emergence, the parts that operate at scales large enough to be represented on the model's grid, in processes slow enough to be averaged over the model's time step. The parts that operate at smaller scales or faster timescales are parameterized, meaning they are represented by simplified equations that approximate their average effect. and parameterization works until the system moves into a regime where the approximations break down. This is where the current moment becomes genuinely difficult to think about clearly, because the models are not wrong in the way that a broken clock is wrong. They are wrong in the way that a map is wrong when you take it into terrain that the cartographer never surveyed. The map is accurate for the territory it describes, it has simply run out of territory. The signals that are accumulating in the observational record are suggesting, with increasing consistency, that the climate system is moving into terrain the models were not built to describe. Not dramatically, not all at once, but persistently, across multiple independent lines of evidence, in a direction that is consistent with the system having crossed, or being in the process of crossing, thresholds that were expected to matter at higher levels of forcing than we have yet reached. This is not a fringe position. It is showing up in the mainstream literature, expressed in the careful language that scientific publishing requires, but present. Papers asking whether climate sensitivity, the amount of warming the system produces in response to a doubling of CO2, is higher than the central estimates. Papers documenting that extreme events are occurring at frequencies that exceed the predictions of models tuned to the current level of forcing. Papers noting that certain feedback processes, particularly those involving clouds, water vapour, and sea ice, appear to be operating with a gain that is larger than the models assumed. The convergence of these signals is what makes the current moment unusual. Any single anomaly can be explained away. A single extreme event can be attributed to natural variability. A single modelling failure can be attributed to a specific parameterization error that will be corrected in the next version. But when the anomalies are appearing simultaneously, in different physical systems at different scales, in different parts of the world, when they are all pointing in the same direction, the aggregate picture becomes harder to dismiss. Let me be precise about what harder to dismiss means in this context. It does not mean certain. Science does not deal in certainty. It deals in probabilities, in evidence, in the weight of competing explanations evaluated against the data. What is happening is that the weight of the evidence is shifting. The explanations that invoke natural variability, instrument error, or modelling artifacts as the primary cause of the observed anomalies are becoming increasingly strained. The explanation that the system is responding more strongly to the forcing than the models predicted is becoming increasingly consistent with the observations, and if that explanation is correct, if the system's sensitivity is higher than the models assumed and the thresholds for non-linear behaviour are lower than the models assumed, then the projections that have been used to set policy, to design infrastructure, to assess risk, to communicate the nature of the problem to the public, those projections are underestimates, not by a little, by an amount that matters. This is not something that researchers discuss lightly. The implications are large and the uncertainty is real, and the last thing anyone wants to do is contribute to a premature conclusion that later turns out to be wrong. But the question is being asked, in the literature, in the conferences, in the conversations that happen after the formal sessions are over. Is the system moving faster than we thought? Is it more sensitive than we assumed? Are we already in a regime that our best tools were not designed to describe? The data is not giving a definitive answer yet. But it is not giving reassuring answers either. And the direction of the residual, the persistent gap between what the models predict and what the instruments observe, is not pointing toward the models having overestimated the response. It is pointing the other way. In 2023, Antarctic sea ice reached a winter maximum that was not just below average. It was below average by an amount that broke the previous record for lowest winter maximum by an extraordinary margin. When scientists calculated the probability of the observed extent given the historical variability of the system, they arrived at numbers that were so small they were difficult to interpret. Some analyses suggested that the probability of the observed conditions occurring by chance, given the historical record, was less than 1 in several million. 1 in several million does not mean impossible, rare events happen. But 1 in several million also means that if you are running a model, and your model does not produce this kind of event, with at least some plausible probability, your model is probably missing something important. And when researchers examined their models, they found that the 2023 Antarctic sea ice extent sat entirely outside the distribution that even the most aggressive warming scenarios their models could produce. The Antarctic sea ice loss has implications that go well beyond sea ice. Sea ice acts as a lid on the ocean below it. When it is present, it prevents the exchange of heat between the ocean and the atmosphere, and it keeps cold, dense water circulating in the patterns that drive the global ocean circulation. The global ocean circulation is not just a curiosity for oceanographers. It is one of the fundamental mechanisms by which heat is distributed around the planet. It moderates the climate of Europe. It influences the monsoon systems that supply fresh water to billions of people. It drives the upwelling of cold, nutrient-rich water that supports the marine ecosystems at the base of the ocean food chain. When you remove sea ice from the equation, or dramatically reduce it, you change the surface energy budget of the Southern Ocean. You change the rate at which heat is exchanged between ocean and atmosphere. You potentially alter the density of surface waters in ways that affect the sinking that drives the deep circulation. The models struggle to capture these dynamics at the level of precision that the observations now demand. What makes this particularly challenging is the timescale. The deep ocean circulation operates on timescales of centuries to millennia. Changes in the drivers of that circulation today may not manifest fully in observable circulation changes for decades. The system has inertia, but inertia cuts both ways. Once changes are set in motion, they are also slow to reverse. The thermal mass of the deep ocean means that heat absorbed at the surface today will be influencing the atmospheric energy budget for centuries after the surface conditions that created it have changed. There is a word that comes up repeatedly in conversations with the scientists who study these long time-scale dynamics. The word is committed. The Earth is committed to a certain amount of future change regardless of what happens to emissions today, because the heat that has already been absorbed by the ocean has not yet fully expressed itself in the surface temperature and atmospheric dynamics it will eventually drive. The lag between forcing and full response is real, and it is long. What we are observing in the atmosphere today is not just a response to what is happening right now. It is, in part, the delayed response to changes in ocean heat content that began decades ago. This has a practical implication that is rarely communicated clearly. When scientists project future conditions, they are projecting a trajectory whose near-term destination is, in some meaningful sense, already determined. The decisions made in the next few years will matter enormously for what happens in 2075 or 2100 or 2150. They will matter less for what happens in 2035 because 2035 is coming regardless, and what it looks like is substantially a function of what was already in the system before any decision made today could take effect. This is not a counsel of despair, it is a call for precision in how we think about what action can accomplish, and on what timescale. The near-term trajectory is largely set. The longer-term trajectory is genuinely open. And the difference between a 2-degree world and a 3-degree world, which may sound small in absolute terms, is vast in terms of the frequency and severity of events like the ones we have been discussing. Let's talk about what happens to precipitation. Rain and snow do not simply increase or decrease uniformly as the atmosphere warms. The relationship between temperature and precipitation is governed by a property of water vapor called the Clausius-Clapeyron relation, which describes how much more water vapor the atmosphere can hold for each degree of temperature increase. The answer is roughly 7% more per degree. This matters because when that water vapor eventually condenses and falls, the precipitation event is more intense than it would have been in a cooler atmosphere. But the relationship between atmospheric moisture and precipitation is not as simple as more moisture equals more rain everywhere. The dynamics that actually trigger precipitation, the uplift mechanisms, the convective instabilities, the passage of frontal systems, those dynamics are changing in ways that are geographically highly variable and difficult to predict at regional scales. What the models consistently project is a pattern sometimes described as wet gets wetter, dry gets drier, meaning that the regions that already receive substantial precipitation tend to receive more of it, while regions that are already dry tend to get drier. But the reality is more complicated than this slogan suggests. The distribution of precipitation within a season is changing as well as the total amount. With more of the precipitation falling in fewer, more intense events and longer dry periods in between, this pattern has profound implications for how water systems work. Infrastructure built to handle moderate precipitation events of a predictable frequency now faces events that fall outside its design envelope. Watersheds that historically recharged gradually during long, gentle rain seasons now receive the same total precipitation in shorter windows of extreme intensity, producing flooding during the event followed by deficit conditions as the water runs off before it can infiltrate the soil. The agricultural implications alone are staggering. Crops are calibrated not just to total moisture, but to its distribution through the growing season. Irrigation infrastructure designed for the historical pattern now faces demands that the pattern no longer reliably delivers. What is particularly unsettling about the precipitation changes is that they are occurring against a backdrop of changes in the water cycle that extend all the way up to the anomalies in the upper atmosphere that we discussed earlier. If the atmosphere is genuinely carrying more moisture at all altitudes, if the transport pathways for that moisture are changing in ways the models do not fully capture, then the precipitation events that express that moisture may be more intense, more localized, and less predictable than even the adjusted model projections suggest. There is a set of observations that researchers have been making about the vertical structure of precipitation events that reinforces this concern. In the most intense convective storms, the kind that produce rapid flooding and severe hail, instruments have been measuring precipitation rates that exceed what the theoretical constraints on storm dynamics would predict. A storm system draws in moisture from the surrounding atmosphere, processes it through the convective engine, and releases it as precipitation. The rate at which that process can occur is constrained by the dynamics of the system, by how fast it can ingest moisture, and how efficiently it can convert that moisture to precipitation. When the observed rates exceed the theoretical constraints, it implies that either the theoretical constraints are incomplete, or the system is drawing on moisture sources at a higher rate, or from a larger volume than simple models assume. Some atmospheric scientists believe the explanation lies in the coupling between the convective storm and the broader atmospheric moisture environment. In a warmer, more moisture-laden atmosphere, the gradient of moisture available to a storm extends over a larger area, meaning the storm can effectively access more moisture than its immediate environment would suggest. The storm and the moisture field around it are not independent, they interact, and the interaction is stronger when the atmospheric moisture content is higher. This is another feedback, another self-amplifying loop, and it is one that standard model parameterizations of convection tend to underrepresent. The practical consequence is what meteorologists are increasingly calling compound events, situations where an extreme precipitation event coincides with saturated soils from previous events, or with high river levels from snowmelt, or with infrastructure that has been compromised by an earlier event and has not yet been repaired. The return periods, the statistical estimates of how often a given level of flooding or storm damage can be expected, are calculated on the assumption that events are approximately independent of each other. When the atmospheric dynamics create conditions that make extreme events more likely to cluster in time and space, those return period estimates become unreliable. Insurance actuaries have been struggling with this problem for several years. The assumption of event independence is baked into the statistical framework that underlies catastrophe modeling. When that assumption breaks down, the models overestimate diversification benefits and underestimate correlated losses. The reinsurance industry, which is essentially the global backstop against catastrophic risk, has been quietly signaling its concern through pricing. The cost of reinsurance for certain categories of risk, particularly for weather-related catastrophes in certain geographies, has risen faster than the underlying claims history would justify if you were only using the historical record as your guide. The industry is pricing in a shift. It is pricing in the possibility that the future does not look like the past. When the people whose financial survival depends on accurately modelling risks start diverging from the historical record, it is worth paying attention. Let me take a step back from the technical details for a moment, because there is a human dimension to this story that tends to get lost in the discussion of model parameterizations and probability distributions. Every one of the anomalies we have discussed has a human face. The Lytton heat dome killed hundreds of people in a region that had no cultural or infrastructural framework for what the temperature was doing. Air conditioning rates in the Pacific Northwest were among the lowest in North America because the climate had never required it. First responders were overwhelmed. Hospitals were treating heat stroke in patients who had never experienced heat like that in their lives, and whose bodies, trained by decades of temperate living, had no physiological preparation for it. The town of Lytton itself burned to the ground the day after setting its temperature record, when the drought conditions and heat-driven atmospheric instability combined to drive a wildfire through the community in less than 15 minutes. There is a particular cruelty in extreme events that fall outside historical experience. People do not know to prepare for them. Governments do not have protocols for them. Infrastructure is not designed for them. The warning systems that exist were calibrated for the range of events that had occurred before, and when an event falls outside that range, the warnings are inadequate. The response is inadequate, and people pay the price of the inadequacy with their lives. This is not a new observation. The mismatch between infrastructure and emerging reality has been a consistent theme in discussions of climate adaptation. But what is changing is the timescale on which that mismatch becomes deadly. When the change in extremes is gradual, institutions have time to notice, adapt, upgrade. When the change involves the kinds of step jumps that the last few years have documented, institutions that were built on historical baselines can find themselves dangerously out of date within a single decade. The city of Phoenix, Arizona provides a particularly vivid illustration. Phoenix is already among the hottest major cities in the world. It has built an entire culture and economy around managing extreme heat. It has systems for notifying vulnerable populations during heat events, cooling centers, protocols for outdoor workers, public health infrastructure calibrated for temperatures that would constitute emergencies in other places. And yet in the last several summers, Phoenix has recorded stretches of consecutive days above a certain temperature threshold that exceeded anything in its records, and the mortality data from those periods suggests that even the extensive infrastructure built for a hot city was not fully prepared for the level of sustained heat it encountered. If Phoenix, which has had a century of motivation to build heat resilience, is hitting edges it did not anticipate, the implications for cities in South Asia, in sub-Saharan Africa, in the Middle East, cities that may be approaching wet bulb temperature thresholds that represent a physiological ceiling on human survivability, are deeply concerning. The wet bulb temperature combines heat and humidity in a way that reflects the actual physiological stress experienced by a human body trying to cool itself through sweating. Above a certain wet bulb threshold, the body cannot lose heat fast enough through evaporative cooling, even in shade, even at rest, and death follows within hours. The threshold at which this becomes fatal was long thought to be a wet bulb temperature of 35 degrees, a number derived from theoretical calculations. Researchers have more recently suggested that the practical limit may be lower, that heat stress becomes incapacitating before the theoretical maximum is reached, and that the combination of heat, humidity, exertion and age can push the physiological ceiling well below the textbook number. The number of hours per year during which wet bulb temperatures in certain tropical regions exceed values that were historically extremely rare has been increasing. Observations from Pakistan, from the Gulf Coast of the Persian Gulf, from parts of India, have begun to document wet bulb readings that approach or briefly exceed levels that no human population was adapted to cope with. The models project these regions will see further increases, but the same issues with model calibration that apply to the other anomalies we have discussed apply here. If the feedbacks are stronger in reality than in the simulations, if the moisture content of the lower atmosphere in these regions is higher than the models predict, if the heat island effects of rapidly expanding urban areas are underrepresented, then the projections may underestimate both the frequency and the severity of events that place human life at direct physiological risk. This is one of the reasons that some researchers who study human exposure to climate extremes have stopped framing the problem purely in terms of global averages and long-term projections. The global average is a useful summary statistic for describing the overall energy state of the system. It is not a useful number for understanding what a specific community in a specific geography is going to experience on a specific summer afternoon. The tail of the distribution is what kills people, and the tail is exactly where the model uncertainties are largest and where the gap between model predictions and observations has been most dramatic. There is a body of research that has emerged in the last decade, quiet but important, that tries to understand how the extremes in the tail of the distribution relate to the mean. In a simple statistical world, if you shift the mean of a distribution upward, you shift the whole distribution, and the tail, the region of rare extreme events, moves by the same amount. Climate change would then produce proportional increases in extreme events. But the atmosphere is not a simple statistical system. The distribution of extreme events is not well described by a normal bell curve. It has a fat tail, meaning extreme events are more common than a Gaussian distribution would predict. And as the mean shifts, the tail can move disproportionately, because the physical processes that drive extreme events interact non-linearly with the shifting background conditions. The consequence of fat tails and nonlinear physics is that a relatively modest shift in the mean state of the atmosphere can produce a very large increase in the frequency of events at the extreme end. This is not theoretical. It is being observed. Events that were historically expected once every 50 years are occurring once every decade. Events that were expected once every 100 years are occurring once every 20. The recurrence intervals are collapsing, and they are collapsing faster than simple scaling from the mean would predict. One of the more striking illustrations of this comes from flood hydrology. Hydrologists build what they call flood frequency curves, statistical relationships between the magnitude of a flood and its probability of occurrence. These curves are fit to historical data. Infrastructure is designed to handle a specific return period flood. A bridge might be designed for the 100-year flood. A levee might be designed for the 500-year flood. The economic logic is straightforward. You invest more in protection against more damaging events, weighted by their probability. When the frequency curve shifts, when what was the 100-year event becomes the 20-year event, infrastructure built for historical statistics becomes dangerously inadequate without anyone changing a single design specification. The bridge that was built to handle a once-in-a-century event is now, in terms of actual risk, 5 times more likely to be tested within its design lifetime. The levee that was specified for the 500-year event now faces conditions that the updated frequency curve would classify as the 100-year event. This is not hypothetical. Flood insurance programs in numerous countries have been quietly repricing their actuarial tables to reflect observed shifts in flood frequency. And the repricing is generating political conflict because communities that have held flood insurance for decades at a certain premium are now facing dramatic increases that reflect the updated probabilistic reality. The political conflict obscures the physical reality. The physics does not negotiate. There is a related problem in the way that rare events cluster in time. In a purely random statistical process, extreme events are distributed through time approximately uniformly. If the 100-year flood occurs today, the probability of it occurring again next year is the same as it would have been in any other year, 1%. The past event does not make the next event more or less likely. But in a physical system that has memory, where the occurrence of one extreme event changes the conditions that govern subsequent events, this statistical independence breaks down. The drought that dries out the soil increases the probability of the next heat wave. The heat wave that depletes soil moisture increases the probability of the next wildfire. The wildfire that removes vegetation increases the probability of the next landslide. These cascade connections mean that in the physical world, extreme events can cluster in ways that exceed what probabilistic models based on independence would predict. Insurance modelers call this accumulation risk, and it is one of their central concerns. When events accumulate, when multiple disasters strike the same region in rapid succession, the recovery capacity of the affected community may be overwhelmed in a way that each individual event would not have caused in isolation. Infrastructure that survived the first flood is weakened and fails in the second. Emergency responders who are stretched by the wildfire are not fully reconstituted when the flooding begins. Economic resources that were drawn down by one disaster are insufficient to absorb the next. The frequency of these compound, cascading sequences in the historical record was low enough that planning systems could treat them as exceptional, as outliers requiring extraordinary response rather than as scenarios requiring systematic preparation. The evidence of the last several years suggests that exceptional is becoming regular in some geographies, and planning systems built on historical frequencies are not keeping pace. Let me shift to something that does not fit neatly into the framework of atmospheric physics, but that connects to the anomalies we've been discussing from a different angle. There is a growing body of work on what researchers call attribution science, the attempt to determine whether a specific extreme weather event was made more likely, more intense, or more severe by long-term changes in the climate system. Attribution science is relatively new. The statistical and physical methods for answering these questions rigorously have been developed largely over the last 15 years, and the sophistication of the methods has been increasing rapidly. The basic approach involves running large ensembles of climate model simulations, some representing the world as it actually is. With the full history of human greenhouse gas emissions and other forcings included, and some representing a counterfactual world, a world that was never industrialized, a world without the additional heat being trapped in the atmosphere. By comparing the statistics of extreme events in these two ensembles, researchers can estimate how the probability of an event like the one they are studying has changed. The results have been striking. For the Pacific Northwest heat dome event, attribution studies concluded that an event of that severity was virtually impossible without long-term climate change. The phrase used in the published analyses was essentially unimaginable in a world that had not warmed the way our world has. For certain record-breaking rainfall events, for certain marine heat waves, for certain fire weather conditions, the attribution analyses have found similar results, not just more likely, fundamentally transformed in probability. But here is the part of the attribution science story that is less often discussed. When researchers compare the actual event to what their models say the event should have been, accounting for all of the long-term changes, they sometimes find that the event was still more extreme than the models predicted. The event is consistent with attribution in the sense that the models agree it could not have occurred in a pre-industrial climate, but the event's specific magnitude still exceeds what the post-industrial models produce. The attribution tells you the change is real. The residual tells you the change is larger than the models capture. This has begun to affect how attribution scientists communicate their results. The early papers in the field were cautious about claiming that warming had made any specific event impossible in the pre-industrial world. The language was about probability ratios, about events becoming 10 times or 50 times more likely. More recent work has become more comfortable with saying that certain events would simply not have occurred without long-term warming, and the community is increasingly aware that even these attributions are, in a sense, conservative, because the models they are using to make the comparison may themselves be underestimating the amplification of extremes. Attribution science has also produced something that is philosophically significant, even if it is rarely discussed in those terms. It has provided a basis for assigning causal responsibility for specific harms to the emissions that drove the climate change. If the probability of an extreme event was increased by a quantifiable amount due to human activities, and that extreme event caused specific documentable harm, then there is a logical chain connecting the emissions to the harm. Several legal cases around the world are now exploring whether that logical chain can support liability claims, whether companies or governments whose emissions contributed to a documentable increase in the probability of a harmful event bear some legal responsibility for the consequences. The law moves slowly, the science is moving faster. But the convergence of attribution methodologies with legal frameworks is one of the more consequential developments in how human society is beginning to grapple with the physical reality of what the atmosphere is doing. There is a different kind of anomaly that belongs in this discussion, one that operates not in the physics of the atmosphere or ocean, but in the biology that lives in both. Ecosystems respond to climate in ways that are deeply integrated with the physical dynamics we have been discussing. Forests regulate moisture, both locally through transpiration and regionally through their influence on precipitation patterns. The die-off of large areas of forest, whether from drought stress, from insect outbreaks triggered by warmer winters, or from direct fire, removes that moisture regulation function. The same change in temperature and moisture that stresses the forest can trigger conditions under which the forest cannot recover once disturbed. The forest becomes a source of heat and aridity, rather than a moderating influence. This kind of ecosystem tipping point has been documented in several regions. The southern Amazon has been showing signs for more than a decade of transitioning from a carbon sink to a carbon source. The system is so large and so important to regional moisture dynamics that a significant dieback of Amazonian forest would alter rainfall patterns not just over the Amazon basin, but over agricultural regions of South America that depend on moisture recycled by the forest system. The feedback between land cover and precipitation is strong enough in that region that deforestation and climate stress can push the system toward a drier equilibrium that makes recovery even harder, a reinforcing loop that researchers have described as a critical vulnerability. In the boreal forests of Canada and Russia, warming temperatures have been enabling beetle populations to overwinter that previously died back during cold winters, producing outbreaks of tree mortality on scales that dwarf historical experience. The standing dead wood from these outbreaks is both a fire hazard and a carbon source, as the organic material that was locked in living biomass decomposes or burns. The interaction between insect-driven mortality and fire creates conditions where large areas of boreal forest transition from forest to shrubland or grassland, with very different carbon storage capacity and very different influences on the regional energy and moisture budget. The loss of permafrost, which covers enormous areas of the Arctic and subarctic, is another biological physical feedback that operates on timescales relevant to the present. Permafrost is soil that has remained frozen continuously for at least 2 years, and in the deepest Arctic deposits for tens of thousands of years. Locked within it is an enormous reservoir of organic carbon, plant and animal material that accumulated and was preserved in frozen conditions over geological time. As permafrost thaws, that organic material becomes available to microbial decomposition, and the decomposition releases carbon dioxide and methane into the atmosphere. The rate at which permafrost is thawing has been accelerating in ways that have exceeded some projections. Ground temperatures in many Arctic regions have been rising faster than air temperatures, due in part to changes in snow cover and vegetation that alter how much solar energy is absorbed by the surface. The structural collapse of permafrost, subsidence events where the ground literally sinks as the ice within it melts, has been occurring in areas that had stable permafrost within living memory. Infrastructure built on permafrost, roads, pipelines, buildings, is experiencing rapid deterioration in some regions as the ground beneath it shifts and settles. The carbon release from permafrost thaw represents one of those feedbacks that was included in climate models, but may have been underestimated in magnitude. The older estimates of the permafrost carbon feedback relied on relatively simple representations of the decomposition process. More recent work has found that certain pathways of carbon release, in particular the release from deep permafrost as it thaws and becomes available to the abrupt thermokarst processes that can release carbon very rapidly, were not well represented in the older models. The updated estimates of permafrost carbon feedback are larger, meaning the system is likely to warm more than the older models suggested, simply from this one feedback that was already in the models but was being calculated too conservatively. There is a broader pattern here that keeps reasserting itself across different parts of the climate system. When researchers update their estimates of a feedback, when they get new measurements or develop better models of a specific process, the updates tend to go in one direction. They find that the feedback is stronger, not weaker, than previously estimated. The water vapour in the stratosphere is higher than expected. The sea ice loss is greater than projected. The permafrost thaw is faster than predicted. The soil carbon release is larger than modelled. The frequency of extreme precipitation events exceeds what the return period statistics suggested. This is not to say that every update goes in the direction of more warming, more disruption. Science is not unidirectional. There have been processes where updated estimates provided more reassurance. The sensitivity of vegetation to carbon dioxide enrichment, for instance, appears in some models to provide more carbon uptake than earlier estimates suggested. Some aerosol forcings have been revised in ways that imply slightly less net warming. The uncertainty genuinely runs in both directions. But when you step back and look at the overall pattern of where the surprises have been in the last decade, they have consistently been in the direction of the real world responding more strongly, more quickly, more extremely than the previous best estimates suggested. This pattern itself carries information. It suggests that the models, sophisticated as they are, have been systematically biased toward caution, not out of dishonesty or political motivation, out of the reasonable scientific instinct to be conservative in the face of uncertainty, to not make claims that outrun the evidence. The problem is that when reality consistently surprises you in one direction, the conservative assumption is no longer conservative. It is an underestimate dressed up in the language of caution. There is a category of atmospheric behaviour that has not come up yet, and it belongs in this conversation because it represents some of the clearest evidence that the models are missing something important about how the system distributes energy across the planet. Atmospheric rivers are long, narrow corridors of concentrated water vapour in the lower atmosphere. Typically thousands of kilometres long and a few hundred kilometres wide, that transport enormous quantities of moisture from the tropics toward the mid-latitudes. When an atmospheric river makes landfall, particularly against a mountain range that forces the moist air to rise and cool rapidly, it can deliver rainfall measured not in centimetres, but in metres over the course of a few days. The flooding and landslides that result can be catastrophic. The parts of the western United States that depend on winter precipitation for their water supply depend on atmospheric rivers for a significant fraction of that precipitation. They are both a hazard and a critical resource. The behaviour of atmospheric rivers in a warming atmosphere is a topic of intense current research. The warmer, the lower atmosphere, the more moisture an atmospheric river can carry, because warmer air holds more water vapour. This simple thermodynamic argument suggests that future atmospheric rivers will be wetter and potentially more damaging when they do occur. But the dynamics of where and when atmospheric rivers form, how they steer toward landfall, and how they interact with the terrain, involve complex interactions between sea surface temperatures, the jet stream, and large-scale atmospheric circulation patterns. All of those interactions are changing simultaneously. What researchers have been documenting in recent observational records is a pattern of atmospheric rivers that seem to be delivering precipitation totals that exceed even the updated projections for a warmer atmosphere. The events that hit California in the winter months of recent years produced flooding and infrastructure damage that was notable not just for their scale, but for the degree to which operational forecasts, even those run only a day or two before the event, underestimated the precipitation totals. The forecast was for a severe event. The reality was for a catastrophic one. The gap between forecast and observation was not in the category of normal forecast uncertainty. It was in the category of the event falling outside the range of outcomes the model was generating. The operational forecasters who deal with this in real time are not the same people who publish research papers about model parameterizations. They are people making decisions about whether to issue evacuations, whether to close highways, whether to alert downstream communities. When their models underestimate an event, the consequences are not an abstract contribution to scientific uncertainty. They are decisions made on incomplete information, warnings issued too late or at too low a severity level. People caught in floods they were told were coming but were not told were coming at the level they arrived. This is the sharpest edge of the gap between model performance and observed reality. It is not just an intellectual problem about the accuracy of equations. It is a practical problem about the ability of human systems to respond to physical events that consistently exceed the envelope their predictive tools were built for. The research community is deeply aware of this. There has been significant investment in understanding the mechanisms behind the forecast busts, as operational meteorologists call them, the specific events where the model performance was worst. One consistent finding is that the events where models perform worst tend to be the events involving the strongest coupling between different scales of atmospheric motion, between the large-scale flow pattern that steers the atmospheric river toward landfall and the mesoscale processes that determine how the moisture is distributed and released when it arrives. The models represent each of these scales, but the interaction between them is parameterized, approximated, not resolved, and the approximations appear to break down most severely exactly when the coupling is most intense, which is precisely when the event is most extreme. There is deep irony in this. The events that matter most for human safety are the ones that are hardest to forecast. And they are hardest to forecast because their dynamics sit at the intersection of processes the models handle separately. The atmosphere does not handle them separately. It solves them simultaneously, with full coupling, and the result is something the models miss. The solution in principle is to run models at high enough resolution that the relevant interactions are resolved explicitly rather than parameterized. The computational cost of doing this globally, in real time for operational forecasting, remains prohibitive. Research models have been pushed to resolutions that capture some of these dynamics, and the results are encouraging. The high-resolution simulations do better. They do not fully close the gap, but they reduce it. The problem is moving those capabilities into operational practice at the speed demanded by the urgency of the problem. This tension between the frontiers of research capability and the requirements of operational practice is not unique to meteorology. It shows up everywhere that fundamental science has to be translated into real-world application in domains where the stakes are high and the timescales are short, but it has a particular sharpness in the context of atmospheric anomalies, because the consequences of the gap are measured in lives and infrastructure, and the ability of communities to survive events that exceed their preparation. Let me tell you about something that happened at a research station in Greenland, because it illustrates the physical reality of one of the more alarming trends in the cryosphere. The Greenland ice sheet is the second largest body of ice on Earth, after Antarctica. It holds enough fresh water that if it melted completely, global sea levels would rise by roughly 7 meters. Nobody expects that to happen on any timescale relevant to current human planning. The question that is urgently relevant is how much the Greenland ice sheet, will contribute to sea level rise over the next several decades, and how that contribution might be distributed in time. Steady, gradual contributions can be planned for. Contributions that arrive in pulses, driven by dynamic instabilities in the ice flow, are much harder to manage. In the summer of 2019, temperatures over the Greenland ice sheet were dramatically above normal, and the melt that resulted was extraordinary. The total ice loss in that single summer exceeded anything in the observational record. More recently, instruments on and above the ice sheet have been documenting a pattern of surface melt that extends further into the interior of the ice sheet than historical records show, and that persists for longer periods within each melt season. The ice itself is not a passive responder to atmospheric temperature. It has its own dynamics. Meltwater that forms at the surface can drain through the ice sheet through vertical conduits called moulins, reaching the base of the ice and lubricating the contact between the ice and the bedrock below. This lubricating effect can accelerate the flow of ice toward the coast, increasing the rate at which ice calves from marine terminating glaciers into the ocean. The coupling between surface melt and ice dynamics represents exactly the kind of feedback that is difficult to represent fully in models. What the ice flow measurements have shown over the last decade and a half is that the contribution of dynamic ice loss, ice that flows rapidly into the ocean, rather than melting slowly in place, has been larger than the purely thermodynamic contribution in some years. The total from Greenland has repeatedly exceeded projections that were considered to represent the central estimate of likely loss. The distribution of outcomes in the model ensembles had the observations inside the spread, but consistently toward the upper end, toward the more aggressive estimates. The real world was tracking the high-end scenario. The implications for sea level rise projections deserve more public attention than they receive. The uncertainty in sea level projections is not symmetric. The processes that could cause sea level rise to exceed projections are better identified and more physically plausible than the processes that could cause it to fall below projections. The fat tail of the sea level distribution is on the high end. Infrastructure planning that uses the median or even the 95th percentile of sea level projections may be inadequate if the physical reality tracks the tail. Coastal cities are making decisions right now about the scale and nature of flood defences that will need to function for 50 or 100 years. The engineering standards that guide those decisions depend on sea level projections, with a specific horizon and a specific probability attached. When the physical system is consistently producing outcomes at the upper end of the projection range, the question of which probability to plan for becomes less about statistical conservatism and more about survival. A flood defense built for the median sea level scenario that is overwhelmed by a tail scenario is not a statistical failure. It is a physical catastrophe. There is a city in Bangladesh that provides a particularly sobering context for this problem. Dhaka has a population of more than 20 million people. It sits in the delta of several major rivers, a geography that has historically made it extraordinarily fertile and that has supported dense human settlement for thousands of years. It is also a geography that makes it one of the most vulnerable places on Earth to the combination of sea level rise, changes in monsoon intensity and timing, and increased cyclone activity in the Bay of Bengal. The infrastructure of the delta has been built around historical flood levels. Annual flooding is not just expected, but essential in the traditional agricultural system, a renewal of soil nutrients that has sustained the delta for centuries. What is not sustainable is the combination of increasing intensity of flooding events, changing timing of monsoon delivery, intrusion of salt water into freshwater systems driven by sea level rise, and the subsidence of the delta itself as groundwater extraction removes the subsurface support. Dhaka is not unique. It is representative of a category of megacities in low-lying deltaic or coastal settings that face compound vulnerabilities from multiple simultaneous physical changes. The people who live in these cities did not create the emissions that are driving those changes. The distribution of physical risk does not correspond to the distribution of historical responsibility for the atmospheric composition that is producing it. This asymmetry is one of the central moral and political challenges of climate change, and it does not have a clean resolution. What it does have is a practical urgency. The decisions that will determine whether those cities can survive the next 50 years are being made now in engineering offices and planning agencies and financial institutions, often without adequate information about the upper end of the physical scenarios those decisions need to be robust against. One of the things that is not often discussed about climate science is the degree to which it is, at its core, a problem of cascading complexity. The atmosphere is complex, the ocean is complex, the cryosphere is complex, the biosphere is complex. Each of these systems has internal dynamics that are nonlinear and sensitive to initial conditions, and they are all coupled to each other, exchanging energy, moisture, chemical species, and information in ways that propagate perturbations across system boundaries in ways that are not always predictable from knowledge of any individual system alone. The scientific literature reflects this cascading complexity in its structure. Papers on atmospheric anomalies cite oceanographic papers, which cite glaciological papers, which cite ecosystem papers, which loop back to atmospheric dynamics. The anomalies we have been discussing are not independent. The stratospheric moisture anomaly, the ocean surface temperature anomaly, the sea ice anomaly, the jet stream behavior, the extremes in precipitation and temperature, they are all connected, all part of a coupled system that is being pushed in a coherent direction simultaneously across multiple components. The challenge for communication is that the coupling is hard to explain without losing the audience in the technical details, and the technical details are where the genuine uncertainty and the genuine evidence both live. There is a temptation to simplify the story into a single clear cause and a single clear effect. The atmosphere warms, extremes increase, ocean warms, sea levels rise, permafrost thaws, carbon is released. These statements are true as far as they go. But they omit the coupling, the feedbacks, the interactions between systems that are producing the excesses and residuals that we have been discussing, the ways in which the real world is outrunning the simple linear story. The more honest and more unsettling account is the one that keeps showing up in the research, multiple physical systems changing simultaneously, the changes reinforcing each other across system boundaries, the combined effect producing outcomes that exceed what any single system analysis would predict. The atmosphere is not just getting warmer, it is getting more energetic in ways that interact with a warmer ocean, a more destabilized cryosphere, a more stressed biosphere, and a more moisture-laden upper atmosphere, in ways that are physically coherent but that the models are still in the process of learning to capture. There is a community of researchers who have been working on what they call early warning signals. The idea comes from the mathematics of dynamical systems, and it has a beauty to it that is worth pausing to appreciate. When a system is approaching a critical transition, a tipping point beyond which it will shift to a fundamentally different regime, it often exhibits certain statistical signatures in the time series data that describe its behavior. The system becomes sluggish. It loses its ability to recover quickly from small perturbations. The time it takes to return to its baseline after a minor disturbance gets longer and longer. In the statistical record, this shows up as increasing autocorrelation, the behavior at any given moment looking more and more like the behavior just before it, and increasing variance, the fluctuations getting larger. These signatures are called critical slowing down, and they have been documented in laboratory experiments and in mathematical models of tipping systems across many fields. The question researchers have been asking, with considerable methodological care, is whether these signatures are detectable in the observational record of the climate system. Some of the answers have been concerning. In records of Atlantic Ocean circulation variability, statistical analyses have found signatures consistent with critical slowing down over the instrumental record of the last century. The analysis is technically difficult, and the interpretation is contested as it should be in science. But the signature is there, visible in multiple independent datasets, examined using multiple independent methods, and it points in the direction that the theoretical framework predicts it would point if the Atlantic circulation were approaching a critical transition. The Atlantic circulation is not a peripheral component of the climate system. It is the mechanism by which warm, salty surface water moves northward through the Atlantic, releasing heat to the atmosphere and moderating the climate of northwestern Europe and the North Atlantic region, and cold, dense, deep water returns southward. The strength of this circulation has varied over geological time, and there have been episodes in the geological record where it has weakened dramatically, with profound effects on regional and global climate. The concern is not that the circulation will stop in the next decade. The concern is that the statistical fingerprints of a system approaching instability are already visible in the data, and that if those fingerprints are genuine early warning signals rather than statistical artifacts, the system may be closer to a transition than the dynamical models suggest. The honest scientific response to this finding is not to run the scary headline. It is to take the signal seriously, to invest in better monitoring, to develop better mechanistic understanding of what is driving the statistical patterns, and to design the modelling tools needed to tell the difference between a genuine early warning signal and a pattern that resembles one for other reasons. All of that work is happening. It is just happening more slowly than the pace at which the observational record is accumulating. There is a philosopher of science named Naomi Oreskes who has written extensively about the sociology of how scientific consensus forms and how it is sometimes resisted. One of her observations, drawn from a careful reading of the history of climate science and of the tobacco and health debate before it, is that manufactured uncertainty has been one of the primary tools used to delay action on scientifically well-established findings. The strategy does not require disproving the scientific consensus. It only requires keeping enough doubt in circulation that the threshold for action never quite seems to be met. That pattern is worth keeping in mind when evaluating the discourse around the anomalies we have been discussing. The genuine scientific uncertainty about specific mechanisms and specific magnitudes is real. Researchers who are honest about what they do not yet know are not retreating from the central findings. They are doing the work of science properly. The uncertainty about whether the stratospheric moisture anomaly is explained fully by the Tonga eruption or requires an additional explanation does not mean there is no anomaly. The uncertainty about the precise mechanisms behind jet stream stalling does not mean the stalling is not occurring. The uncertainty about the exact magnitude of the permafrost carbon feedback does not mean the feedback is not real. In a complex system with genuine uncertainty at the level of mechanisms and magnitudes, the appropriate response to that uncertainty is not to treat it as reason for inaction. It is to treat it as reason for precaution, precisely because the direction of the uncertainty is consistent. When the surprises keep coming from one side of the distribution, when the real world consistently exceeds the model projections rather than falling short of them, the rational response to that asymmetry is to take the upper end of the uncertainty range more seriously, not to average it away. This is how engineers think about risk. When you are designing a structure and your analysis shows a distribution of possible loads, you do not design for the mean. You design for a point in the tail, for a level that provides a margin against the possibility that your analysis is wrong in the direction that matters. The riskier the consequences of failure, the further into the tail you design. The atmosphere is not a bridge, but the principle of designing for the tail, of taking the upper end of the physical range seriously rather than assuming the middle will hold, is one that the evidence of the last several years gives us considerable reason to adopt. There is something else worth understanding about the scale of what is happening, something that does not reduce to a set of anomalies or probability distributions, but that has to do with time. Human beings are poor intuitive reasoners about exponential processes and about phenomena that operate on timescales that exceed lived experience. The atmosphere has been accumulating greenhouse gases for 2 centuries of industrialization, with the rate of accumulation accelerating over time. The heat that has been added to the system is not spread evenly through time. The ocean, which absorbs the vast majority of the excess heat, has a massive thermal capacity that delays the expression of that heat in surface temperatures and atmospheric dynamics. The system is in the process of catching up to the energy imbalance, and the catching up is not complete. This means that the anomalies we're observing now are not the final state. They are a stage in a continuing transition. The atmosphere that produced the Lytton heat dome, the record ocean temperatures, the Antarctic sea ice collapse, the anomalous mesospheric clouds, is not yet in equilibrium with the forcing that has been applied to it. It is still adjusting. Some of the adjustment is fast, operating on timescales of years to decades. Some of it is slow, operating on timescales of centuries. The slow adjustment is locked in. The fast adjustment is ongoing. The practical implication is that the baseline against which we compare future events is itself moving. An event that is extreme relative to the conditions of the last decade may be unremarkable relative to the conditions of the next decade. The extreme of today becomes the new normal of tomorrow. This is not a metaphor. It is a physical description of how the system is evolving. The temperature record that was shattered in Lytton in 2021 will eventually not be a record. It will be a warm summer day. This does not mean events will continuously escalate without limit. The system is not heading towards some catastrophic endpoint without any stable states along the way. Complex physical systems have attractors, configurations they settle into, and as the forcing changes, the system will settle toward new attractors. But the transition between attractors, the period of adjustment that the system is currently navigating, is precisely the period of greatest instability, greatest deviation from historical norms, greatest difficulty in forecasting and preparation. We are in that transition period right now. The anomalies are a symptom of it. The failure of models to fully capture the extremes is a sign that the system is in states it has not been in before, within the period of instrumental observation, states that the models were not fully trained to represent. The scientists are working urgently to understand it better. The physical processes are not waiting. There is a particular kind of expertise that becomes valuable during periods of transition, when the systems that societies depend on are evolving faster than the institutions built around them can adapt. It is not the expertise of the specialist who understands one part of the system deeply. It is the expertise of the integrator, the person who can move between disciplines, who can hold the complexity of multiple interacting systems simultaneously, who can see the patterns that emerge from coupling rather than only the patterns within individual components. Climate science has been building this kind of expertise for decades through programs that train researchers to work at the interfaces between atmosphere and ocean, between physical climate and ecosystems, between the dynamics of the cryosphere and the behavior of the circulation. That community of integrators is generating the most important insights about what is actually happening. Their papers are not always the ones that make the evening news. They appear in journals that require technical training to read. Their conclusions are qualified in the way that honest scientific conclusions are qualified, with probability ranges and sensitivity analyses and lists of caveats. But underneath the caution is a picture that is becoming progressively clearer. The climate system is responding to the forcing it has received with more sensitivity, more coherence, and more speed than the previous generation of models and projections suggested. More sensitivity, more coherence, more speed. These three words are worth sitting with. More sensitivity means that the relationship between the amount of forcing applied and the degree of change in the system is larger than previously estimated. The atmosphere heats more per unit of carbon dioxide than older sensitivity estimates suggested. The extremes increase more per degree of mean warming than simple scaling would imply. More coherence means that the changes are not occurring independently in different parts of the system. They are correlated, reinforcing, organized in a way that reflects the coupling between components. When the ocean surface heats anomalously, the atmosphere above it responds in ways that amplify rather than dampen the ocean's departure from normal. When the jet stream stalls, the soil dries out. The soil dryness amplifies the heat. The heat influences the circulation patterns that determine how long the stall persists. The coherence of the changes makes the system harder to predict, because small errors in representing the coupling can produce large errors in the eventual outcome. More speed means that the timescale of the transition is shorter than earlier estimates suggested. Changes that were projected to arrive by the end of the century are arriving now, decades ahead of schedule. The earlier projections were not dishonest. They were based on the best models available at the time, models that, as we have seen, consistently underestimated the sensitivity, the coherence, and the speed of the system's response. The people who will live with the consequences of that underestimation are already alive. Some of them are living in the places most immediately affected. Some of them are the atmospheric scientists who will spend the rest of their careers trying to close the gap between the models and the reality the models are describing. And some of them are the billions of people who are not scientists and not in the most vulnerable geographies, but who live under the same sky, breathe the same air, depend on the same water cycle, and the same chain of physical processes that extends from the ocean surface to the mesosphere and back again. The sky above our heads is not a backdrop. It is a system in motion, and that motion is changing. The instruments that measure it are running hot. The models that simulate it are running behind. The gap between the two is where the work is happening right now in research groups and computing centers and instrument arrays and satellite missions, all directed at the same question. What is actually happening up there? The honest answer, as of now, is that the system is more energetic than projected, more sensitive than modeled, changing faster than predicted, and producing extremes at a frequency and magnitude that consistently exceeds what the tools built to describe it were designed to handle. The work of closing that gap is urgent, and it is ongoing, and it is being done by people who understand with full seriousness what is at stake in the answer. What the rest of us can do in the meantime is refuse to accept the comforting simplification, refuse to treat the models as the reality rather than as approximations of it. Refuse to use the uncertainty in specific mechanisms as a reason to discount the coherence of the overall pattern. The anomalies are real. The direction is consistent, the residuals are not shrinking, something is happening to the sky. We are watching it happen. The question is not whether we are paying attention. The question is whether, and how quickly, the understanding being generated by the people who watch it most carefully will translate into the decisions being made by the people who live under it every single day. That translation has never been more urgent, and the sky has never been less willing to wait.